Welcome to your chemistry online class. In last class, we discussed about the VSEPR theory, that is valential electron pair repulsion theory. There we have seen some limitations. It cannot explain the type of bond in some compounds. So the another theory came. This is known as valence bond theory, VB theory. So in this theory, it is proposed by Hitler and London, and later it is further developed by Linus Pauling and by explain the concept of hybridization. So in today's class we are going to discuss about VB theory and hybridization. So there are several assumptions in the VB theory. Those are: all bonds are localized bonds formed between two atoms by the donation of an electron from each atom. For example, uh, for the bond formation, each atom will donate one electron. That is, if you take hydrogen will having 1s1, another hydrogen having 1s1. So this one electron will donate by each atom. This is the first assumption. And using this valence bond theory, we can describe the covalent bond and electronic structure of molecule. Based on this valence bond theory, we can understand the covalent bond, what type of covalent bond will be there, and electronic structure of molecule. And the other assumptions are, this theory assumes that electrons occupy atomic orbitals, individual atoms within a molecule, and that the electrons of an atom are attracted to the nucleus of another atom. That is, if we take electrons, we know electrons are in the atomic orbital, that is S shell, P shell, D shell, etc. These are atomic orbital. So in the case of this atomic orbital, the valence electron are combining in the formation of a bond. So in the valence electron, they attracted by the nucleus for of other atom. For example, if we take Na is the nucleus of an atom, E is the valence electron of that atom, Nb is the nucleus of atom B, Eb is the electron of the atom B. Here, what is this assumption is Na attracted Eb, Nb attracted Ea. Then, so if we take here, we have seen that using valence bond theory, it can explain the covalent bond. So there are mainly two types of covalent bond that we can explain. Before that, a covalent bond is formed by the overlapping of two half-filled valence atomic orbital of different atoms. So covalent bond is formed. Covalent bond is formed by the combination of two half-filled orbitals. That is, the orbital which having single electron. So single electron can represent by this symbol. So this two single atom will combine to form a covalent bond. So for this purpose, they will overlap each other. They overlap each other and get paired. So these two will overlap, and they will combine and they pair. So due to this, the stability increases. So if an atom having a single electron, it is unstable in nature. So they will form like this and they become more stable. And if greater the extent of overlapping, the stronger will be the bond form. And according to the direction of overlapping, for example, orbitals can overlap in different direction. Based on that, we can classify covalent bond. So we can say that covalent bond is directional in nature. So mainly before going to that, there are three types of orbitals, that is s orbital, p orbital, d orbital. Both these having different shape. S orbital is in spherical shape, p orbitals are in dumbbell shape. So it is a different shape. So we can see that. So there are two types of covalent bonds based on the pattern of overlapping as follows. That is sigma bond. There are two types, sigma bond and pi bond. Sigma bond is the overlap, the atomic orbitals overlap will occurs linearly. For example, if we take an atom's nucleus, if it is an atom, this is also another atom. If they'll overlap linearly in the through the nucleus center, then we can call it as a sigma bond. This is called as linear overlap. If they are overlapping linearly, then we can call it as a sigma bond. And pi bond. Pi bond is through parallel overlap. For example, parallel overlap we can show by this is an orbital and it is another orbital. If by sidewise they will overlap, then we can call it as a parallel overlap. Such bonds are called as pi bond. So sigma bond, the covalent bond formed due to overlapping of atomic orbital along the internuclear axis, that is linearly. So it's a symmetrical. So based on the types of orbital overlap, the sigma bond further divided into three. For example, if one s orbital and another s orbital combine to form sigma ss bond. For example, here you can see one this valence orbital having only one electron. So it is unstable, it is unstable. For stability, what they will do? They will combine together to form, they paired each other and became stable. So here this is s orbital, it is spherical in shape. So these two combine to form sigma ss bond. Then sigma sp bond. Sigma pp bond, that is two p orbital. This is p orbital, this is p orbital. They combine to form sigma pp bond. And if one s orbital and p orbital combine to form sigma sp bond. These are the three types of sigma bond. And pi bond. Pi bond is by sidewise overlapping. Here you can see the sidewise overlap. So the electron density will be the above and below of the internuclear axis. This is the nucleus. So here it is sidewise overlap, hence it is not strong as much of sigma bond. And the s orbital only form sigma bond, whereas p, d, f orbitals will form both sigma and pi bond. Then we can see some illustration. H2 molecule. For example, if we take H2 molecule, the electronic configuration of hydrogen atom is 1s1 in ground state. So in its valence shell, it is having only one electron. So it is unstable. First, what will they will do for the stability? It will combine each other and form sigma ss bond. It is linear. And for example, Cl2 molecule, in its valence shell, we can see its atomic number is 17. So if you write the electronic configuration, we'll get, if we draw that, we'll get half filled p orbital. We know in its valence shell it contains 7 electrons. For example, 3s2, 3p, 3s2, 3p5. All other are in the inner shell. So valence shell, it is having 7 electrons. 5 plus 2, totally 7. So it is 3s2, 3p5. So if we check the p orbital, it is arranged through one. First we have to consider of Bohr principle, Pauli's exclusion principle and all. So first electrons will filled, half filled, then the pairing will occur. So p having 5 electrons, so 3 electrons already occupied. So then 4, 5. So the single electron will be in the px. So p orbital is in 3 type, px, that are Px, Py and Pz. So in Pz only one electron. So what will happen is Pz1 of one chlorine and Pz of another chlorine combined to form paired electron, that is it is sigma pp bond. And HCl molecule, if you take HCl molecule, 1s orbital of hydrogen, 3pz orbital of chlorine combined to form sigma sp bond. Then O2 molecule, if we take O2 molecule, oxygen, in oxygen valence electron 6 electrons are there. These are here 2s2, 2px2, 2py1, 2pz1. So it's py and pz having having one electrons each. So it will form sigma pp bond and pi pp bond. Here you can see, because this will be linear, so linear sigma pp bond is in sideways, they will overlap, then pi pp bond. Similarly, N2 molecule, 3 unpaired electrons are there, so they will pair, so it will form sigma pp, pi pp, pi pp. Then we'll move to hybridization. What do you mean by hybridization? Hybridization is the intermixing of two or more pure atomic orbitals to form a new atomic orbital. If two atomic orbitals having same energy, they will combine to form an identical and degenerate new type of orbital. This process is known as hybridization. And this new orbital formed is known as hybrid orbital. So during hybridization, atomic orbitals are with different characters. For example, S and P can combine. SPD can combine together. So different nature also combined each other, but they should have the same energy. So based on that, there are mainly 6 type of hybridization: sp hybridization, sp2 hybridization, sp3, sp3d, sp3d2 and sp3d3. So first we can see sp hybridization, that is s orbital and p orbital combined to form sp hybrid orbitals. So you can see this is the new hybrid orbital, sp hybrid orbital. So if it should be having equal energy, so it will combine, and there should be the bond angle between these will be 180 degree and linear structure. So that this we have seen in BSCPR theory. There if we take linear structure, then it is bond angle will be 180 degree. So if we take this compound, the new hybrid orbital having 50% of S character and 50% of P character. If you move to sp2 hybridization, one s orbital, one p orbital and another p orbital. So you will get trigonal planar structure, and bond angle is 120 degree. Here this hybrid orbital having 33.3% of S character and 66.6 of P character. Then sp3, similar S and 3 P orbital, that is Px, Py and Pz will get sp3 hybridization. Bond angle will be 109.28 minutes. S character 25% and P character 75%. Similarly, sp3d, s orbital and 3 p orbital and 1 d orbital. If they have same energy, they will become identical and degenerate form. So it will arrange in a trigonal planar arrangement. That is 3 will arrange in a trigonal plane model. Here you can see trigonal plane, and 2 orbitals will be in the above and below the plane. The bond angle here will be 90 degree, here it will be 120 degree. So the sp3d hybrid orbital having 20% of s character and 60% of p character and 20% of d character. sp3d2. In sp3d2, 1 s orbital, 3 p orbital and 2 d orbital. They will arrange in octahedral symmetry. The bond angle will be 90 degree each. We can visualize it in the base of two orbitals arranged in a square planar and like this. Two orbitals will be above and below the plane. sp3d3. 1s, 3p and 3d. Bond angle will be 72 degree. So, if based on number of electron pair, we can understand or we can identify the hybridization. If a compound having two electron pair, then the hybridization will be sp. Shape will be linear. The molecule having linear shape. For example, beryllium hydride, BeH2, etc. And if three electron pair are there, the hybridization will be sp2. For example, 1s and 2p. So 2 plus 1 is 3. This geometry will trigonal planar. For example, ammonia molecule NH3. Then 4. Here 1s and 3p. So 3 plus 1 4 electron. And tetrahedral or pyramidal or bent, any model there will be CH4 etc. We can say. Then sp3d similar 5 electron pair will be there. Trigonal by pyramidal, for example PCl5 etc. Then if there are 6 pair of electron, that will be having octahedral geometry such as SF6 etc. These are all about hybridization. Okay, thank you.